This is lecture 16, and till the last class we had discussed some reactors. So, that is the last thing that we had done. So, we discussed constant pressure reactor, constant volume reactor, and also well stirred reactor. Now, there is another very important reactor which is called a plug flow reactor, but then I'm thinking that maybe you can look this up yourself from a textbook. So, you can look up Turns's book and go through the discussion on plug flow reactor. So, I am leaving this to you so that we can save more time to discuss other kinds of combustion processes. So, today we will start discussing combustion waves. So, we will start discussing not exactly a reactor, but a situation where there is a combustion wave propagating through a mixture. And a combustion wave can be actually a detonation wave, or it can be a deflagration wave, detonation or deflagration. Now, this will slowly become clear to us, but we will have a simplified discussion of this sort of a situation. So, let us see what the physical configuration is. If we have a situation like this, where we have a mixture and we ignite the mixture here, then maybe we will get a combustion wave. So, this is a combustion wave, which will propagate in this direction. So, this tube has a fuel air mixture, and then you have a combustion wave which propagates from my right hand side to my left hand side. So, this way, and again as we know, we can write unburned here. So, this is a mixture through which the combustion wave has not propagated so far, and on this side we can write burned. This is already burned, and the conditions here are like rho 1, T1, P1, and the condition on this side are rho 2, T2, P2. Now, what are these? This is density of the unburnt mixture, this is temperature of the unburnt mixture, this is pressure of the unburnt mixture. Similarly, for the burnt, rho 2, T2 and P2. Now, the unburnt mixture and the burnt mixture will have some velocities. So, we can call those velocities V1 and V2, V1 and V2. V1 for the unburnt side, V2 for the burnt side. So, 1 subscript 1 identifies the unburnt side, subscript 2 identifies the burnt side. So, you have V1 and V2. Now, what are we trying to do? We will do a 1D analysis of this situation, and we will assume steady flow. We will assume that the area is constant. So, this area that we are talking about, this area is constant. So, constant area, and we will assume ideal gas. We will assume again for the sake of simplicity constant and equal specific heats. We will neglect body forces like gravity, and we will also assume adiabatic condition. Now, let us think about this for a minute. Let us say we have this tube which is filled up with a fuel air mixture. So, it can sustain combustion, and you have ignited it. So, there is a combustion wave that propagates from right to left, as I told you. So, 1 is the unburnt side, 2 is the burnt side. So, this is easy to understand. Now, what is a combustion wave? Now, combustion wave is this zone here, which propagates. Now, is this a collection of some material particles? So, if it moves from here to somewhere over here, do we say that the same particles have moved from here to here? No. So, the answer to that is no, because what has happened is at this point of time particles here were reacting, fuel and oxygen molecules were reacting. Around here now a new set of particles are reacting, because these have already burnt. These have already burnt, and then the combustion wave has moved here, and then are some new set of particles are burning. So, this is like a wave. Okay. These are not material particles as such, this is a wave. So, this wave has moved. So, we call this a combustion wave. Now, this combustion wave, as you saw just a few minutes back, can be a detonation wave or can be a deflagration wave. Okay. So, there are two possibilities. Now, what is a deflagration wave? Deflagration wave is a flame in the normal sense in which we understand flames. So, this is a low speed reaction zone. So, the reaction zone, a deflagration is a flame which is a reaction zone which will move relatively slowly, a few centimeters per second or maybe at most a few meters per second. Okay. Whereas, if you talk of a detonation wave, it can move at supersonic velocities. So, this is a very fast combustion wave. Detonation is a very fast combustion wave. Now, you might ask, looking at all this at this stage, you might ask that when do we get deflagration and when do we get detonation? So, that is a hard thing to say right now, but it will depend on various operating conditions like the pressure, temperature, density, etc., but also it will depend on the boundary conditions. If you have this tube which I have drawn here, it has two boundaries, it has two ends. Now, depending on whether the ends are open or closed, the dynamics of the combustion wave can change. Okay. Exactly how, we do not know, but that is what we are trying to see. So, that is the whole idea. So, we would like to see when we get a slow combustion wave and when we get a fast combustion wave. That is the purpose of our analysis. Now, our analysis is going to have limitations, because we are saying that this is only a one dimensional analysis for steady flow. In an actual situation, if you have this fuel air mixture and if you have ignited it, you are getting a combustion wave. That wave may not be one dimensional, number one, and number two, it may not even move at a steady rate. Okay. So, this is an approximation. If you look at that combustion wave that I have drawn, then it is like I have drawn it more like a flat surface. Okay. But there is no guarantee that it will be like a flat surface. In fact, it might have complicated structure, and it may be entirely three dimensional. So, it may not be very likely to say that it is one dimensional, but that is the best that we can do at this stage. In this course, we will be able to do just a one dimensional analysis, and we are also assuming it to be steady, knowing fully well that it may not be steady, in the sense that the combustion wave that you see, it might accelerate also. Okay. So, it is moving from my right to left, and then so it is going from here to here, still moving this way, right, but it can accelerate. So, as of now we do not know whether it will accelerate or not, but to keep matters simple, we are saying that we will do 1D analysis and we will also do steady flow. Constant area, that is another assumption, but that is easier. We can say that it is constant area. So, we have assumed 1D fixed tube, so maybe constant area also. Ideal gas, good enough, probably. Constant and equal specific heats, again specific heats are not constant with temperature, but we are assuming it. Neglecting body forces, maybe body forces are really not important. Gravity is in many cases not that important. Then we also assume it to be an adiabatic condition, in the sense that there is no heat transfer from outside to this tube or from the tube to outside. These are the assumptions that we are making. Now, you can also see that for the unburnt we are writing rho 1 T1 P1. So, just one set of values. That means unburnt here and the unburnt here are being characterized by the same values, same rho 1 T1 P1. Similarly, the burnt here and the burnt here and the burnt here are all at rho 2 T2 P2. So, these are the assumptions that we are making. So, it is like it is this burnt mixture is all homogeneous and it is at equilibrium. So, it has the same uniform composition, same uniform temperature, the same uniform density everywhere. So, that is another assumption. So, the purpose of our analysis, we will do some analysis. What are we trying to understand? We are trying to understand whether we will get a deflagration or detonation, and whether we can say something about the speed at which the combustion will be moved, right. I have already told you, since I have done the analysis before, that this combustion wave can be subsonic or it can be supersonic. Okay, so it can go really fast. We will not be able to do a full analysis, we will not have a very good understanding, a complete understanding of deflagration and detonations, but we will have some basic understanding of how these combustion waves moves, what are the kinds of velocities, and when we get a deflagration, when we get a detonation, we will understand to some extent, not fully, okay, because this simple analysis cannot tell us that much. Now, what sort of analysis we will do? The analysis we will do will involve some set of equations. So, it will involve, as you can understand, it will involve mass conservation, momentum conservation, and also energy conservation. Okay, mass, momentum, energy. So, we are assuming 1D steady flow. So, we will be able to write for mass conservation, we will be able to write okay. So, rho 1 U 1 equal to rho 2 U 2 equal to m dot. So, this is this combustion wave, and what are U 1 and U 2? I wrote V 1 and V 2 few minutes back, isn't it? V 1 and V 2 were the velocities here and here. Now, we will assume some velocities U 1 and U 2, these are velocities of the unburnt and the burnt with respect to an observer who is on the combustion wave. So, if you are on the combustion wave, right, if you have an observer on the combustion wave, he will see velocities U 1 and U 2. Okay, you will see velocities U 1 and U 2. So, V 1 and V 2 can have directions like this, but U 1 and U 2 will have directions like this. This is U 1, this is U 2, correct? V 1 means velocity of the unburnt gas, V 2 means velocity of the burnt gas. Okay. Now, V 1 and V 2 are velocities which are seen from a coordinate system which is not on the flame, from a stationary coordinate system. So, imagine doing this experiment, you are holding this tube, you have a mixture, then you have this combustion wave which is propagating, right. So, you are seeing it from outside, you will see velocities V 1 and V 2. Whereas, if we place an observer on the combustion wave, then you will get velocities U 1 and U 2. Is that correct? So, you will also note that the sense of V 1 and V 2 are different from the sense of U 1 and U 2. That is understandable. I am assuming that V 1 is towards the left, V 2 is also towards the left, V 1 and V 2 towards the left. Okay. And in that case, U 1 is, we can assume U 1 to be towards right and U 2 to be towards right. Okay. Which way is the combustion wave moving? It is moving in this direction. This is the movement of the combustion wave. So, we can give that a name also. This velocity can be VW. So, there is a stationary reference frame from where you will see the combustion wave moving from right to left at a speed of VW, and in that stationary frame you will see unburnt velocity V 1, burnt velocity V 2. Now, place yourself on the combustion wave. Will you see U 1 and U 2 like this? Correct? Why are the directions opposite? Yeah, so we can assume that if you are sitting on the flame, it will look like, to you the flame is stationary. Suppose you are sitting on the flame. In fact, I should not call it a flame, combustion wave. Okay. So, if you are sitting on that combustion wave, you will see that the combustion wave is stationary with respect to you, because you are sitting on the combustion wave, and it will appear that the unburnt gas is moving towards you to get consumed. Okay, so that's U1, and then we have also this same sense written for U2. Okay, so we are choosing these two directions for U1 and U2, and based on all that we can say that rho 1 U1 has to be equal to rho 2 U2. So imagine again this, you can imagine this sort of a control volume around that combustion wave. Rho 1 U1 is moving into the combustion wave, rho 2 U2 is moving out of the combustion wave. So rho 1 U1 equal to rho 2 U2. That is because it's steady, right? It is steady, so whatever moves in, the same mass goes out. This I have written as m dot. Strictly speaking, I should write m dot double prime. Okay, strictly speaking, I should write it m dot double prime. Now, what's the unit of rho 1 U1? Kg per meter squared second. Kg per meter squared second. So kg per meter squared second, as I said, strictly should not be written as m dot, because m dot gives you the unit of kg per second. Okay, but I am not writing the double prime. Okay. So let us write this one m dot double prime, and then say writing m dot double prime as m dot for convenience, nothing else, because otherwise I will have to keep writing this double prime everywhere. That is the only reason. So if we do that, then this is m dot. Okay. So this is a steady situation, and that's why the steady situation, that's why rho 1 equal U1 equal to rho 2 U2. Now, if you again take this combustion wave, and if you take this control volume here, then there is P1 acting on this pressure and P2 acting on this. So this P1 minus P2 is resulting in some change in momentum. Okay. What's the momentum here? Momentum flux going into this. Momentum flux, mass flux is rho 1 U1. Mass flux going into this left face is rho 1 U1. So momentum flux should be rho 1 U1 square. So this rho 1 U1 square going in, and there is rho 2 U2 squared going out. So we should be able to write so note that we are not writing equations in differential form. This is like overall integral balance, because on the left hand side it's all uniform U1, on the right hand side it's all uniform U2. Only at the combustion wave this change is taking place. So this is your momentum. So this is momentum, and this is mass, and we will have an energy equation also. So we need this equation 1, that will be helpful. We have this equation 2, and then we will also have equation 3, which is energy equation. So how do we write this energy equation? Again, this combustion wave, right? So how do we write this steady flow situation, energy equation for the steady flow situation from thermodynamics? So your control volume is here around the combustion wave. So something is entering, something is going out, something is coming in, something is going out. How do we write all this? Q dot Cv plus m dot into all that. So it should be something like Q dot Cv plus m dot Hi, actually I here is not the ith species. We have to remember that, isn't it? That's like entering. Okay, hi plus u I squared by 2 plus gzi. That's right. 1 here, 1 here, 1 here. So we write 2. But we'll of course neglect this change in potential energy. We're not even discussing that change. We assume that there's no real change in potential energy, and q dot Cv is 0 because we are considering adiabatic situation. W dot Cv is 0, 0, right? No work done. So yeah, so there's no shaft which will rotate or something like that. So there's this situation only. So we will get m dot on both sides. M dot even can be cancelled. So it's h1 plus e1 squared by 2 is h2 plus u2 squared by 2. Correct. Now let's understand h1. What is h1? It's the enthalpy of, one is for unburnt mixture. So one is for unburnt mixture. H1 is enthalpy for the unburnt mixture, but it is small h. So that means it's per unit mass. Okay. So this should be, h is actually summation yi hi. If the summation is done for state 1, we are considering 2 states, isn't it? One state is the unburnt state, which is 1, and the other state is the burnt state, which is state 2. So this is h is this h1 is summation yi hi on the unburnt side. Okay. And h2 is summation yi hi on the burnt side. Okay. Right. Now let's also think about this in slightly more detail. Hi is the enthalpy of the ith species. Right. So this is HFI plus CPI dt T ref to T. So this is the calorific equation of state. This is how we write that standardized enthalpy. Enthalpy of formation plus the sensible enthalpy change. So we can do that. And what is the assumption that we made regarding CPs? Cp is a constant and Cp is so that means not dependent on temperature and also equal for all species. So we will have H1, which is summation yi hi is equal to summation yi this, which is okay. So these summations are for the since we are writing it for H1, so these summations are actually for the state 1, for the species which exist on the unburnt side. So if it is a propane air mixture, then the species that you are talking about are propane, oxygen and nitrogen. So these summations are over those 3 species. correct. So, strictly speaking, I should write this as Cp1, Cp of the unburnt mixture, but actually we are taking all Cp's to be equal. So, the burnt side mixture Cp for the mixture 2 which is on the burnt side will also be Cp. So, there is no need to write Cp1 and Cp2, correct. So, that is what we get. T can be, yeah, so this can be, that is correct. So, we should write this actually, this can be T1, and our equation was a few minutes back we got this. So, we write summation yi hfi naught plus Cp T1 minus T def this is over 1 correct. So, the Cp T def will get cancelled. So, we will get Cp T1 plus U1 squared by 2 plus summation so this is an energy equation, correct, the same energy equation. Now, it is written in terms of temperature. So, previously we had enthalpy. Correct. So, let us focus on something which we still need to understand little better. We need to understand this term. What is this? Cpt1 is straightforward, E1 squared by 2 is straightforward. E1 is that velocity of the unburnt mixture relative to the combustion wave. Okay, so it is a relative velocity. I hope that is clear by now. And U2 is similarly the relative velocity of the burnt mixture with respect to the combustion wave, and then Cpt2 you understand. So, let us see what this is. So, we are writing this. To understand this, let us think about whether this has some connection to heat of combustion. Do you think it might have some connection with heat of combustion? Something similar? Yeah, so the heat of combustion was what? It was the enthalpy of the reactants minus the enthalpy of the products. And what conditions did we specify then while defining this heat of combustion? Yeah. Yes, the reactant side and the product side temperature and pressures were the same. Yeah. And if you do it at 1 atmosphere and 298 Kelvin, then you get the standard state heat of combustion. Now, looks like you have the enthalpies of formation of individual species, and enthalpies of formation of individual species are actually at 1 atmosphere 298 Kelvin, isn't it? So, we are writing HFI naught. Okay, so this looks like this is somewhat similar to heat of combustion. But what was heat of combustion? It was, let us say heat of combustion has HR, right, and HR is summation Ni Hi bar. Okay, we defined that this is for the reactants, and this is summation. So capital Ni is the number of moles of the ith species. So this is also Mi by Wi into Hi bar. So Mi is the mass of the ith species. In a mixture, the mass of the ith species is Mi. Okay, Wi is the molecular weight of the ith species. So Mi by Wi is Ni, the number of moles of the ith species. And can we give a name to this one? Hi bar divided by Wi. No, molar is Hi bar. Molar is Hi bar. So the molar quantity divided by the molecular weight should give what? Small h of the ith species, isn't it? Because this Hi bar has a unit of kilojoule per kilomole, Wi has a unit of kg per kilomole. So this thing should have the unit of kilojoule per kg. So that means it should be Hi, right? Kg is the molecular weight of the ith species. Kg per kilomole, I mean per kilomole. See, this is, let us say, WO2. Suppose you are talking about oxygen molecular weight. Oxygen molecular weight, what do we say? It is 32 kg per kilomole. Okay. So that kg will come with the kilojoule value of Hi. So it should be able to give you kilojoule per kg of the ith species, which we are calling Hi. Correct? That is why this is Hi and this is Mi. Okay. So this is kilojoule per kg and this is kg. Both the kgs are actually kgs of that ith species. Okay. So we get this, and this looks similar to this, doesn't it? Looks similar. In fact, they will look more similar if we write for Hi, if we write HFI naught. Instead of Hi, we can write HFI naught when we are talking about 1 atmosphere 298 Kelvin, isn't it? Because then there is no Cp term, there is no sensible enthalpy change term. So this becomes this when you are talking about just 1 atmosphere 298 Kelvin. Okay, now this is looking similar to this. What is the difference? The difference is we have summation Yi HFI naught, which is summation Mi by M mixture HFI naught. Okay. So this quantity was the enthalpy of reaction at 1 atmosphere 298 Kelvin. So this is nothing but this enthalpy of reaction, enthalpy of the reactants actually, sorry, this is not enthalpy of reaction, this is enthalpy of reactants, this is enthalpy of reactants divided by the mass of the mixture, okay, mass of the mixture. So if you think about it in this way, you will understand that this is HR, enthalpy of the reactants under standard conditions per unit mass of the mixture, minus this should be, what's the second term should be like? It should be the enthalpy of the products at 1 atmosphere 298 Kelvin per unit mass of the mixture. Okay. So we will give this a name, we will call this a Q. So this is a heat of combustion at 1 atmosphere 298 Kelvin, but written as per unit mass of the mixture. Okay, written as per unit mass of the mixture. Because when we write heat of combustion, often we write in terms of the mass of the particular species. So if we say methane heat of combustion is this much, we actually mean that kilojoule per kg typically refers to the heat of combustion that you get by burning 1 kg of methane. okay, but here it is per unit mass of the mixture. So, that is the difference, but we remember this and we will call this a Q, and if we call this a Q, then looking at the last form of the energy equation that we had, we can actually say that the energy equation is this. This energy equation is this. So, just very quickly let me summarize all those equations. You have seen them before, but mass is rho 1 u 1 equal to rho 2 u 2 equal to m dot. Momentum is and energy is this. So, we are now okay with the equations that we have. We have 3 equations. We actually do not need to write any species equation, because for species on the unburned side we know what the composition will be, because you are choosing the unburned gases yourself. So, you know the unburned composition. For the burnt one, we will assume a combustion model which can be, let us say, based on the amount of air that you are using, products of complete combustion. So, that can be one model, okay. Or you can say that you want to use the equilibrium composition of burnt gases as the product composition, okay. So, we will use that sort of thing to understand what the burnt composition is. So, we do not need a separate equation for species. So, now we have the 3 equations set up. What do we want to do with these equations? Let us recollect what our objective is. We want to see how fast the combustion wave moves, that Vw speed that I mentioned. So, how fast is that, and then also under what conditions you are likely to get a realistic combustion wave, and under what conditions you are going to get a slow combustion wave, and under what conditions you are going to get a fast combustion wave. That is all that we are trying to understand. Again, the caution that you should always exercise is that we are actually talking about this situation as a 1D steady flow, ideal gas, constant area, that sort of thing. In reality, these combustion waves are much more complex. They are often not one dimensional, and they are often not steady. They move, they accelerate, okay. Anyway, so let us see how much this simplified perspective can give us. Now, in order to do these equations, in order to understand what these equations are telling us, we will try to visualize the 2 states, and we will use a coordinate which is like this. So, pressure versus 1 over rho. 1 over rho is specific volume. So, you can write this as a small v also, okay. But I got little used to writing 1 over rho, so I will write 1 over rho here. So, that means you have, let us say, this point which corresponds to 1 over rho 1 P 1. So, that is your state 1. State 1 can be easily plotted, because you have the unburnt mixture with you. You know what its pressure is, because you have kept it at that pressure in that tube, okay. You know the pressure, you know its density. So, you can plot this point 1. Our objective of doing all this analysis with these 3 equations will be to see where point 2 lies, okay. Where does point 2 lie? For that, the first thing we will do is try to combine equations 1 and 2. And if you combine equations 1 and 2, then Let me see whether I can do it here. Okay. Yeah, that's better. All right. So we can write P2 minus P1 So that's combining 1 and 2. So that should be okay with you. Very simple thing. So rho 1 u1 square, it is written in terms of rho 1 u1 whole square divided by 2, divided by rho 1. Okay. So that gives you this, and this tells you that P2 minus P1 So, I have this equation. Now, by combining the mass conservation equation and the momentum conservation equation. So, does it tell you something? Going back to the plot, we are trying to use this plot to gain some idea, to have, yeah. So, this first point is 1 over rho 1 P1. As I said, this point is in your hands, this is your unbound condition. So, what does this equation tell you? I mean, you can see somebody just mentioned gradient. So, P2 minus P1 divided by 1 over rho 2 minus 1 over rho 1 is what? It is the gradient of a straight line, isn't it? So, that is minus m dot squared. P2 minus P1 divided by, if you switch the sign here, 1 over rho 2 minus 1 over rho 1 is minus m dot squared. Okay. So, that means your point 2 should be such that P2 minus P1 divided by 1 over rho 2 minus 1 over rho 1 should be minus m dot square, correct? So, what does this tell you? Yeah. So, if I draw from one, if the point is here, suppose the point 2 is here, will that work? It will not work, isn't it? Because this has what kind of a slope? It has this line has a positive slope, but this tells you that if you combine mass conservation with momentum conservation, it tells you that state 2 has to be such that this line is actually excluded, correct? So, what lines will be excluded? If you think about extending this one and this one, all these lines will be excluded, right? So, these are all gone. So, that means these are not valid, this part is not valid, whereas you can probably have lines which were more like this, okay, or like this. So, the combination of these two relations, this expression, combination of the mass conservation and the momentum conservation, gives you Rayleigh line relation. Okay. So, already we have learned something. We have learned that state 2 cannot lie in this quadrant. That is the purpose. The purpose of our analysis is actually not going to be solving all the equations. but to be able to say something about state 2. So, we have already been able to say something that state 2 cannot be in this region. Now, I will have to give you some homework, small piece of work based on this. This should be verified by you. I am trying to save some time here. So, the Rayleigh line of this, and the same thing can be written in terms of a Mach number. So, the Mach number is u1 by c1. u1 you know, so that is that unbound side relative velocity. c1 is the speed of sound, so this is the sonic velocity. So, c1 is root gamma r t1, okay. Actually r1 t1, r1 is the characteristic gas constant of the unburnt mixture. So, this is a certain c1. So, u1 by c1 gives you a Mach number, and with just a little bit of work you can show that this Rayleigh line relation which you have got here can be written as gamma m1 squared so this is the Rayleigh line relation in terms of the Mach number.
Why is it R1?
R1 is a characteristic gas constant of the unburnt mixture. So, 1 for the unburnt mixture.
Will it be different? The CP has been taken as constant.
CP, but this R1 is in terms of molecular weights, no. So, we can analyze that. Let us see, as of now let us keep this as R1. Okay. We only analyze the CP part of it, we did not say anything about
characteristic gas, not the universal.
Not the universal gas constant. Okay. So, we have this one, we will try to verify this. This is like homework, check this out. You do not have to show it to me, but this is just a few steps which you should do. And so, this is the energy equation. Now, as I said, we are trying to do everything on this plot. Okay. We already plotted possible Rayleigh lines on this plot. We said some are not possible, then there are some others which are possible. So, we have some idea. Now, can we convert this energy equation, maybe combine it with something and prepare another equation which is in terms of P and 1 over rho. Is it possible to do that? So, we do not want U1, we do not want U2, we do not want T1 and T2, we do not even want Cp. Okay, Q can be there, Q is just a number, Q can be there. So, can we change all this in terms of pressure and 1 over rho? It can be done, because you have this Cp T1, so you have Cp, and one way can be that you replace Cp in terms of maybe a gas constant R, okay. And once you do that, then you get RT. So, I am just giving you broad idea, you get RT, and RT can be written in terms of P by rho, P equal to rho RT. So, it can be done that way. So, we can replace Cp, we can bring in R, and then we will get RT. Once we get RT, we will get P by rho. That is one option. And the other thing is we will also have to replace it u1 squared by 2 and u2 squared by 2. Now, here also I think since we are running out of time today, I will just give you a broad idea. So, Cp minus Cv is R. So, that means Cp correct. So, for this Cp, if we use gamma R divided by gamma minus 1, then you will get RT1 here and RT2 there. Okay. Actually, R1T1 and R2T2. And then we can replace R2T2 as P2 by rho 2, R1T1 as P1 by rho 1. Do that. Then this can be obtained. Jumping steps, as I told you. They can verify, not here, maybe at home. And we also have from this we can write got these two. Okay, just slight manipulation, that's all.
So u1 square can simply be written as m dot square by rho 2 square.
Yeah, but this is like playing some trick to bring in 1 over rho 1 everywhere. Actually, you will see that this works because ultimately
So that will also give us 1 by rho 1.
Yeah. Here, this one. This is rho 2 by rho 1. This is P2 minus P1. P2 minus P1 divided by rho 1. So, we are not bringing in m dot. Okay, we are not bringing in m dot. So, this will work fine. So, we will just close in about a minute or so. Before that, let me tell you what we are doing here. So, up to this is fine. This is fine. This we got by bringing in gamma R divided by gamma minus 1. So, we got this. Now, this term is replaced with the help of these two. Okay. So, if you do all that, that means you bring this and this here, and you already have this, you have this, then we can actually get this you can get this after some work, some simplification. But you just have to tell me whether this sounds possible or not. This should be possible. Yeah. So, we will stop here and This is in fact, this has a name. This is called the Rankine-Hugoniot relation. So, this has this combination of energy conservation and also mass conservation, because we wrote P1 plus rho 1 U1 squared is equal to P2 plus rho 2 U squared. We took the help of that to arrive at this. So, it has the energy conservation as well as the momentum conservation built into it. So, it also has implicitly the fact that m dot is equal to constant. So, it actually has all three in it, and you have to verify this. You have to verify whether we are getting this or not. Whether we are getting this or not, please verify. And we will meet tomorrow and see what we can do with this equation. Thank you.